So welcome to discussion 10. So in today's discussion, we'll do some small signal analysis, basically for resistance. So we'll do some resistance analysis for small signal models of BJT and MOSFET. And we'll also do some high frequency responses for BJT and MOSFETs. Basically, we'll try to find what's the mid-band gain and also the high frequency FH for some transistors. And since Professor has covered BJT in lecture, so in this discussion, we'll do MOSFETs instead. So first, we'll do two examples in this discussion. The first one is about small signal resistance. So I'll give you like 30 seconds to read through this problem, and then I'll solve it. So this one is asking to calculate the small signal resistance of R1 and R2. So basically, we want to calculate small signal resistance in this direction, and also looking from the collector and also looking from the emitter. And you can see the biasing circuit has already been ignored. That's why we have a DC directly connect to the B. So for small signal models, the first step, if you want to do any small signal models, is to remove the DC components. That means you have to either short your DC voltage source or open your DC current source. So for the DC bias, like what you have saw in class is something like this, we'll just short the DC current source to the ground, so out to the ground. That's why we just have a ground directly connected to the base for small signal models. So try to make sure to remember this for small signal models. We have different, we use different methods to remove current and voltage source. So let's go back to this problem. So for part A, we want to find R1 and R2 when VA equals to infinity. So where did we use VA for? You should recall those components. GM is IC over VT, where VT is 0.026 or 0.05 volts, 0.25 volts. And your R pi is beta over GM, and VA is used for RO. So RO is VA divided by IC. So when VA equals to infinity, you will have RO equals to infinity, which you can just ignore it. And then for part A, so RO equals to infinity, and we'll find R1 first. For small signal resistance, the first step is always draw the small signal model of your circuit. So the equivalent small signal model for this circuit will be ground to the base. This is our base, and we have R pi. This is our emitter, and we'll have voltage controlled current source, GM, VB, and we'll have RO, which is infinity for VA equals to infinity, so we can just ignore it. There's no RO left. And we have an RE connected to it, and another RC connected to it. So this is the DC voltage source. That's why we have to short it. So RC to ground. And this is our collector. So this is a small signal model for this circuit. And to find R1, if we want to find R1, we have to apply a test voltage Vx to the circuit. And then we want to find what's the current through it. and then your R1 will just be Vx divided by Ix. So R1 is the resistance seen at the collector side. So we have to put our test voltage at the collector side. So we have Vx here, and we want to find what's the Ix. Then your R1 will just be Vx divided by Ix. So let's calculate this. So first, copy this first. Okay, so first, for this part, it's starting from ground and ends at ground. So the voltage of all these two components are 0. There will be no voltage between those resistors, across those resistors. That's why we will have VBE directly to the 0 equals to 0. So your voltage control current source, GM VBE, will be another 0. Basically, it means we'll have an open circuit here. That means all the current Ix can only flows in this direction. So your Ix will just be Vx divided by Rc. And in other words, your R1 equals to Vx divided by Ix will just be Rc. So this is a small signal resistance looking from the collector side when VA equals to infinity. All right, we can move on to the next part. Same, VA equals to RO equals to infinity. And we have, we want to know what's the R2. So looking from the emitter side, what's the R2? Let's put the small signal model again here. So this is small signal model for the circuit on the left. And I want to know what's the resistance. Can you explain again how you know VB equals 0? Oh yeah, let's go back here. So because for this part, we will have, so these two resistors or this path is start from 0, from ground, and it ends at ground. The only like current source or source connected to it is GNVBE, but this is a voltage controlled current source. So this GNVBE depends on the VBE in this branch. So in other words, there's no direct or static DC current or voltage source connected to it. So this one, you can just ignore it. It will not help with this path. So just for this path, it starts from a ground and it ends at ground. So there's no voltage drop across R pi and also RE. That means there will be the voltage will just be 0. So VBE just be 0. In other words, if we do not have a voltage controlled or dependent source here, if we have a, let's say if we have another current source, let's call it ID. So it's not dependent source, so it's not dependent with VBE. In this case, we will have a non-zero VBE value. But for a dependent source like GM VBE, we'll just ignore it. We'll have a 0 VBE instead. Okay, let's come back to this one. So same small signal model as the previous part. But now we want to calculate what's R2, what's the resistance at the emitter. So we'll want to put test voltage Vx here and find Ix. Your R2 would just be Vx divided by Ix. So in the small signal model, that means you have to put a Vx at the emitter node. So plus minus Vx, and we want to know what's the Ix. See, so in this part, your VBE is not 0 anymore because you have a static or an independent voltage source connected to your emitter. You will have a non-zero VBE. So what's the value for your VBE? So your VBE will be ground minus the voltage at node E, right? It will just be Vx. So your VBE will be negative Vx. So your current here will be negative GM Vx. We have to write key CL for this circuit. So for the key CL, let's write key CL at node E, so at the emitter. First, I will have a current flows out of the emitter node. It will be Vx divided by R pi. And I'll have another current flows out of the emitter here. It will be Vx divided by Re, right? And I will have a current flows in because of this current source will equals to which is equals to Gm, a negative Gm Vx. And also I will have an Ix flows in, so plus Ix. This is the key CL we had for the node at the emitter node. So just rearrange this, you have Ix equals to Vx 1 over R pi plus 1 over Re plus Gm. So your R2 will equals to Vx divided by Ix, which is 1 over R pi, 1 over Re plus Gm. So this is the small signal resistance looking from the emitter side for Va equals to infinity, Ro equals to infinity. So part A is done. Okay. Let's do part B then. So for part B, now we have Va is not infinity, it's finite. That means our Ro equals to Va divided by Ic will be finite. We have to consider Ro in this case. In other words, you have to write your Re and R1 and R2 in terms of Ro, Gm, R pi, R1, Rc, Re. So you have to have an Ro term in your expressions. Okay, so for calculating R1, let's calculate R1 first. We always have the same small signal model for the circuit, the same circuit, so same small signal model. Not the same, right? Because we have an Ro now. So I have to add an Ro here. So another resistance added to the small signal circuit. Let's do find R1. You have to put a test voltage at the collector and to find the current Ix. So we are putting the test voltage at the collector side. This is correct. Now we have to write KCL to solve this problem again. So first I'll write my KCL at collector node. So here. And I will make an assumption. I will assume the voltage at the emitter is VE. So I assume the voltage here is VE. Basically, I will need two KCLs. I will need two equations to solve this problem. But I will write my first KCL at the collector, which is I will have my voltage at the collector will be Vx. Yes. So first I'll have current flows out. So Vx divided by Rc. I'll have another current flows in this direction. So it will be Vx minus Ve divided by Ro. Or R0. And then I'll have my current flows in this direction, right? From my current source is GMVBE. And we have to find what's the VBE. So VBE right now, it will be ground minus VE. So it'll be negative VE. So my current in this path will be negative GMVE. And all these currents will equal to Ix. So Ix is a current flows into the node, and we'll have 3 currents flows out of the node. So this are just equal to each other. So the second KCL, I'll do a KCL at the emitter side, at the emitter, so at node E. So at node E, I'll have VE and node E. So first I'll have current VE divided by RE, plus my another current flowing here will be VE divided by R pi. And this will equals to my current here, which is negative GMVE. And also my current flowing into the node is plus Vx minus VE divided by RO. So you have 2 KCL or 2 equations, and you can just representing VE using Vx, and then plug it back to this equation. You can find what's the ratio between Vx and Ix. So to save time, I'll just write down the final answer. But you can try to solve it by yourself. So R1 will be Vx divided by Ix, which is pretty complicated. 1 over RC plus 1 over R naught plus GM plus 1 over R naught times 1 over 1 plus GM R naught plus R naught over R pi plus R naught over RE, I guess. Yeah, that's your final answer. You can calculate it if you are interested. Okay, so this is for R1. So similar for R2. So for R2, we'll put a test voltage at the emitter, Vx, and find Ix. So draw this in the small signal model. So in the small signal model, it will be something like this. You have a Vx and Ix at the collector side. And our R2 will be Vx divided by X. So as similar to the previous calculations, we have to write KCLs for different nodes. So I'll write KCL for these 2 nodes at node E and node C. I'll assume the voltage at node C is Vc, and the voltage at node E will be Vx. So let's write KCL at E first. So we'll have a current here, so it'll be Vx divided by Re. Another current flows out will be Vx divided by R pi. And we'll have current flows in will be equals to Gm VBE, which is Vx minus 0. And also flows in Vc minus Ve divided by, oh, there's no Ve. It will be Vc minus Vx divided by Ro. So the first KCL is done. And then the second KCL will be KCL as a collector side C. I'll have current flows out. It will be Vc divided by Rc. I'll have current flows out in this direction plus Vc minus Vx divided by Ro. And also another current. Oh, I forgot to put Rx in the previous equation. Flows out, flows in. Yeah, we also have an Ix flows in at node E, so plus Ix here. I just forgot this. And for KCL at C, we'll have Vc over Rc, Vc minus Vx divided by Ro, and also Gm VBE here. So it will be Gm, and VBE is Did I make a mistake? Yes. Sorry about that. So maybe here is 0 minus Vx. So I have just reversed the signs. And this is GM VBE. VBE is 0 minus Vx and equals to 0. So 2 KCLs are done. You can just use this 2 to calculate your R2. Let me double check VC over C. Yes, correct. So you can just write using this 2 to calculate your R2, which is Vx over Ix. I'll just write down the answer. It'll be 1 over Re plus 1 over R pi plus 1 plus Gm R naught over R naught, R naught Rc plus 1 over R naught Rc. So if you are interested, you can calculate this by yourself. So the first problem is done. So as you can see, once the VA is not 0 and infinity, so when you have R naught, the resistance, the calculations are become much more complicated. Okay, let's move on to the next problem. Is high frequency responses of MOSFET. So professor has done BJTs in class. So here we are doing MOSFET instead. I'll give you 30 seconds to read this problem, and then I'll solve it. Okay, so as you can see in this problem, the value for CC1, CC2, and CS, so these 3 are not given. So they are just bypass capacitors. So they are usually large, like I'll say 10 microfarads is a reasonable value for them. That means they will only these 3, like CC1, CC2, and CS, will only contribute to your F low, so to your low frequency responses. But we are doing high frequency responses. That means you can just ignore them for your calculations. Ignore means short circuit. So you can just short them for your calculations for high frequency responses. So first, let's find what's the AM. So AM here is the midband, is the cutoff frequency at the high frequency range. The cutoff frequency for CC1, CC2, and CS will be the low frequency range, free frequency end. So for these 3 capacitors, you have to use SCTC. This method, as professor has mentioned in class today, to calculate FL, which is F low. But we are doing high frequency responses. That means you can ignore those large capacitors in your circuit. They are just short circuit. So you can just treat them as short circuit. That's completely fine. So for AM, that's midband gain. So midband, so it's already for frequency greater than F low, right? So for frequency greater than the F low, which is the lower end of your cutoff frequencies, all these CC1, CC2, and CS are short circuit. So let's just draw your small signal model for the circuit with CC1, CC2, CS shorted. VC here, we'll say this is AC source. So let's draw the small signal circuit. So first, for small signal, as I mentioned in previous problems, for small signal, if we want to do any small signal analysis, first you have to remove your DC components, or sorry, DC sources. This is the first thing you have to do, which is short your voltage short your DC voltage source and open your DC current source. So different method for voltage and current source. So for this one, let's see, we have a VDD, which is a voltage source. So just short it to the ground. And that's it. So let's just draw the circuit. So we'll have a plus minus VC AC circuit here. We'll have an RC, and we'll have RG1, RG2 all connected to the ground. So they are in parallel. So we'll have RG1 parallel to RG2, and then to my gate. So I have my gate, which is plus minus VGS. And at my drain, I'll have GM VGS first. And also I'll have RO, right? So I have another RO connected to the source and drain between. And also at my drain, I have an RD connected to the ground. So I have another RD to the ground. At the drain, you also have an RL to the ground. So it will be RD in parallel with RL. And that's done. This is your drain. For your source, so as you can see here, it's directly shorted to ground. So it will be just ground as source. So this is the small signal model for your MOSFET, or small signal model for the circuit on the left. This is a complete model of it. Let me copy this first. Okay, so let's solve it. For the midband gain, oh, yeah, I forgot to mention this. For MOSFET, it also has something like C pi and C mu we learned for BJT. But for MOSFET, it will have CGS connected between gate and source. It will also have CGD connected between gate and drain. So these are two capacitors we have for MOSFET, just like C pi and C mu. But for midband gain, we can just ignore CGD and CGS because these two will not affect your midband gain. You can just remember this. So for midband gain, let's calculate what's V out. So AM equals to V out over VC, right? We can divide this into two parts. Will be VGS over VC times V out over VGS. So what's your VGS over VC? So we want to know what's the VGS over VC. It's just a simple voltage divider. So pretty simple, we can just write it down. So VGS over VC will just be RG1 parallel with RG2 over RG1 parallel with RG2 plus RC. It's simple, it's just a voltage divider. And for V out over VGS, so you can see here, we will have a current source. And your V out will just be, yeah, I'll write down the equation for V out first. So your V out will just be 0 minus the current GM VGS times RO parallel with RD parallel with RL. So it's just Ohm's law. Your V out will just be the current in this branch times the resistance, which is all three in parallel. And your VGS is can be calculated in the previous part, right? So your V out over VGS will be negative GM, RO parallels RD parallels RL. So your final AM will be the product of these two terms. So it will be negative RG1 parallel with RG2 over RG1 parallel with RG2 plus RC times GM, RO parallel with RL parallel with RD. So it's a negative gain. So you can, I will suggest you to remember for MOSFET, like the gain between gate and drain is negative. So if you want to calculate what's the voltage gain between gate and drain, is negative value. But if you want to calculate the gain between source and drain, so from the source to the drain, the voltage gain will be positive. So I'll suggest you to remember this. And the gain between gate and source, I mean, gate and source is close to 1. That's why we call it source follower, because the small signal gain between gate and source are usually 1 or close to 1. You can calculate that. Just some info. Okay, so we are done with AM, the mid-band gain. We can move on to calculate FH. So to calculate FH, we have to do the same OCTC analysis that professor did in class. That means your FH will be 1 over 2 pi will be omega h over 2 pi, and your omega h will be 1 over summation RC. So it's the summation of the time constants for the high frequency circuits, high frequency capacitance. And for this small signal model, I'll pass it here. So things I just talked about. We can ignore CC1, CC2, and CS for high frequency responses. So these 3 capacitors will not contribute to your time constant, contributes to your RC. So for this RC, you just need to care about CGD, CGS, and also C load. So usually the load capacitance may be small, but we don't have RL or CL in this circuit. So you can just ignore CL. So the only 2 capacitors that will contribute to the time constant will be CGD and CGS, with your CGD here. So this is your CGS and your CGD. To do the open circuit analysis, that means for calculating each time constant, you have to open other caps first. That's called open circuit time constant. So you have to open other capacitors first. Let's just say this. So first, I want to know what's the time constant for CGS. I want to know what's the time constant for CGS. So I have to open CGD first to calculate my time constant. That means I have to open my CGD first. There's no CGD, it's open circuit. And then I have to, so this is the first step, open CGD. And the second step is replace your CGS with VX. And then you have to calculate what's the IX and then find your R. This is the second step. And the third step is your time constant will just be R times CGS. So these are 3 steps we used to calculate the time constant for each capacitors. So let's replace CGS with the VX. We have a VX here, plus minus VX. And I want to know what's the current IX, so I can calculate the resistance. So for this part, the first thing you should notice is this part will not contribute or will not affect your IX. It's just not related to each other. At least for this part, it will not affect the IX of your gate and source part. So those 2 will not affect with each other, at least for IX. So we just need to care about this part to calculating the resistance. And your resistance will just be, yes, another thing you should know. For calculating the FH, you also need to remove your voltage source here. So it will be another short circuit. So for your R will be Vx divided by Ix. It's pretty straightforward if you're looking in this direction. those two resistors are just in parallel. So your equivalent resistance will just be R6 and parallels are RG1 and RG2. This is your R. That means your time constant for CGS will just be, let's say, tau CGS will just be R6 parallels RG1 parallels RG2 times your CGS. This is the first time constant you may need to use for the FH. And the second time constant is for CGD. So it is for CGD. So to calculate this time constant is tau CGD. You have to open CGS and also replace CGD with Vx and calculating the resistance, looking from Vx. And then your tau CGD would just be R times CGD. This is the steps you should do for open circuit or OCTC analysis. So open CGD, open CGS, so we'll have no resistance here, no resistance between gate and source, but you will have a Vx connecting between gate and drain. I mean, the polarity of your Vx does not matter. It's okay to put either in either directions. I would just put it here. So I have Vx. I want to know what's the Ix. So my R will be Vx divided by Ix. Okay, let's solve for it. Basically, you have to write KCL again. Professor, I think he has done this in class today. So he just asks you to remember the resistance for CGD or C mu term. For C mu and CGD term, the resistance is usually just let's say this is R1. Also, this is R1. You can remember this. This is R1, and your load is R2. So your R will just be R1 plus R2 plus GM R1, R2 for C mu and CGD. If you want to know that what he said, you can just go back to today's lectures. I think the video is posted. You can check for it. But I will also go through the calculations here, just to make sure you know it. So first, I will have to do KCL for this circuit, always. But I will make one assumption. So to calculating the R, you also have to short your signals. So a short circuit here. I'll make one of my first assumptions. I will assume the voltage here is V1. You can say VG, it's okay. And I will assume my voltage here will be V2. Just two assumptions. So first, write a KCL for V1 or for gate node. The first KCL will be, I have a current here, so it will be V1 over RC plus V1 over RG1 parallels RG2, right? And also I'll have a current in this direction, which is just Ix. Then KCL at V2 will be V2 over RO Okay, I made a mistake. So all these three currents are flows out of the node. So I'll put Vx here equals to 0. And for V2 will be V2 divided by RO plus V2 divided by RG parallels RL. So these are two branches. And also you has Ix flows in. Oh, sorry, let's do VGS first. So I'll have another current flows in this direction will be GM VGS. And their VGS is V1 minus ground. So just be V1. You can plug in VGS to here, if you want. And this 3 current will equals to Ix. So this 3 are flowing out of the node, and this it flows into the node. So these are equal to each other. We have another equation that's the relationship between V1 and V2. We'll have V1 plus Vx equals to V2. So you have these equations, and you can just solve for the R. You can solve it by yourself if you're interested, or just remember it. But this will give you the same result as Professor mentioned. So your Rx, your R, will just be Vx divided by Ix is Gn R sig. I mean, our sig here is Gm R sig, and parallel with Rg1, parallel with Rg2, times your RL, which is RO parallel with RG parallel with RL, plus your R sig parallel with RG1 parallel with RG2, plus RO parallel with RD parallel with RL. Looks complicated, but those two are actually the same. So I would suggest you to remember these formulas. They will save you a lot of time. So you will not need to write a KCL every time for the analysis. It's much simpler. So your we'll use the same one. So your time constant, let's say tau CGD, will just be this R times your CGD. So another time constant is done. So your final FH will be 1 over 2 pi times 1 over, let's say, R CGS times CGS plus R CGD times CGD. So you can just plug in values you calculated before. You have a resistance when only have CGS. You have resistance for CGD. So just plug in values. You can calculate FH, which is 525 kilohertz. So I would suggest you to calculate this if you are interested. But you would, so for homework 9, we have lots of AM and FH analysis for BJTs. So you can do that. You can solve those problems and learn more about the analysis. Basically, they are the same as this problem. So the same method, the same analysis, the same steps. So you can use these discussions to finish your homework 9. And that's all I had for today. If you don't have any questions, you're free to leave. Thank you.